I would like to give a brief introduction about Professor Huang. Professor Huang received his master's degree and PhD degree in the Department of Organic Materials Science and Engineering in Seoul National University. He has authored or co-authored more than 653 papers in international peer-reviewed journals. And those journals has been cited more than 33,000 times with the H index 89. And he has given over 100 invite presentations at the international conference. He also held 130 international or domestic patents. He's a recipient of the Alexandra von Humboldt Fellowship Award in 2004, and the 7th Presidential Young Scientist Award of the Korea government, AP Faculty Excellence Award, Air Products USA, Intron Award, and the Kenyon Arm Award. His current interests include high-K gate oxide, DRAM capacitors, new memory devices, including RRAM, PRAM, ferroelectric materials and devices, negative capacitance effect, and thin film transistors. He's also working actively in the field of neuromorphic computing devices and materials. He served as a general chair of the International ARD Conference in June 2010 in Seoul, and he also authored books entitled Atomic Layer Deposition for Semiconductors through the Springer Publisher, and Ferroelectricity in Doped Hafnium Oxide through the Elsevier Publisher. He's a member of Korea Academy of Science and Technology, National Academic of Engineering of Korea, and a fellow of the Royal Society of Chemistry, UK. On September 1st, 2020, he was selected as the Seoul National University Distinguished Professor, which is awarded to only 8 members among the 2,200 faculty professors in Seoul University. Let's thanks first. Now Professor Huang, the time is you.
Okay, thank you very much, Professor Chen. Happy New Year, everybody in Singapore. And I greatly appreciate your offering me this chance to give a talk on what you have done during the past couple of years for this memristor-based temporal kernel application of some of the RRAM materials or memristors. Most of this work is done by Mr. Yunho Zhang, who is spending his PhD work in my lab. And this work is published listed in this journal. So if you're interested in, please refer to this paper. And I look like this. So let me get started with a brief introduction on what the machine learning or neural network with hardware is for. See, the AI is very well known sort of.
그건 잘 모르겠습니다. 제가 도울 수 있는 다른 부분이 있을까요? 알겠습니다. 웹에서 화이에 대해 찾은 결과입니다. 확인해 보세요.
Suddenly the iPad start to talk to me, so I just shut it off. Well, it's embarrassing. It never happened. So the AI is kind of now a very popular field where the software works, and when it is combined with so-called data science, you see, we could do a lot of new things using computers, which has not been possible in the past when we use conventional computing tasks. The neural network, the very basic or fundamental neural network structure is like a fully connected network in which you input the data here. So like the images or the letter images, and then you classify what it is using this fully connected network at the output layer. But the more advanced or better way to identify what it is using this kind of a convolutional neural network, meaning that the convolution means that you extract the feature of this input image and compressed the features into smaller size of images, and then you do the same thing again, and then you identify what the feature of this convoluted image using this fully connected network, and then you see what the original image is. So it looks like a little bit complicated, but it's actually showed a much better performance than using this kind of raw data to identify what it is. So this is kind of very common network structure, which is being used for many applications in software-based neural network at the moment. But one of the problems with this convolutional neural network is that it cannot identify or the process the time-related image inputs. So if you want to, let's say, identify the languages or some other things that has relationship, time-wise relationship between inputs, you cannot use this kind of CNN. Then you have to find some way to input the time relationship between the inputs to your network. And one of the very well-known network structures is so-called recurrent neural network. And in both cases, we take this kind of networks as a kind of kernel, which is sort of a filter. Now, let me talk about what this filter means. So as I mentioned, for the CNN, you have this raw data, and you apply a filter element here, and then the filter elements actually extract the feature of this raw data and put this number into some certain point, and then if you take away the insignificant bits from the compressed image, then it means you have pooling, and then you got this kind of feature extracted new vector, which is kind of representative of the original image, which was in this case given in two-dimensional image, but in this case you have one-dimensional vector which composed of a feature of this image. Then the fully connected network or the identifying layer identifies what it is. So this is the conventional kind of CNN system. Now, one of the very well-known recurrent neural network is so-called reservoir computing system, RC. What RC means is something like this. But actually, if you look at the literature and see what the RC is, it gives you some kind of complicated words, something like projection into high-dimensional space, or the nonlinear transformation, something like that. So it's not easy to grasp easily, but I guess I can give you some good example of what RC is doing using this schematics. So now here you have this 28 by 28 image of number 8. Now you chop this image into this number of columns. And then you want to, so let me go back to here. You want to project each of these column information into a certain neuron or whatever the reservoir element, which in this case memristor. And then this reservoir, a set of reservoirs or a set of memristors represent this two-dimensional image in one-dimensional vector. And then you identify what this vector is using this readout layer, which is usually a fully connected layer. So in this case, the features are projected from the temporal inputs into a reservoir. Now, you may do not understand what temporal means here because we have these static images. but it will be more clear as I talk more about the feature of this reservoir system. So the reservoir type of application of MNIST has been suggested by I just don't remember his name. Weidu group of Michigan a couple of years ago. And in this case, he shows very nice experimental example how to project this two-dimensional image into one-dimensional vector composed of memristors. So in this case, this is the number 2. And if you chop this number into, let's say, 5 columns, like this one and these ones. So now, if you take this black as a 0 input signal and white as 1 signal, so if you convert this as a 0, 1, 1, 0 into voltage pulses, you will have something like this. So 0, 1, 1, 0. And you see that there is a gap between these two pulses. That's important. Now for the second column, you see there is 3 zeros and 1. So there is 0, 0, 0 pulses and 1 pulse at the end, so which corresponds to this white dot here. Now this third column, you see this pulse must be placed here, and fourth column, the pulse must be here. Now in the last column, the fifth column, there are 4 pulses like this. Now, if you input these pulses into these each memristors, you will see very interesting response of this memristor. Before we go further, let me explain the feature of this memristor briefly. This memristor is a sort of a volatile memristor. So here, once we put this into some sort of on state or low resistance state and let it go with time, and then the conductance decays, so the current decays with time. So this is sort of a characteristic feature of this memristor they've used for this work. Now, this chart shows the readout current when these inputs comes into each of the memristors. So now let's see first case, this 100 case. So it means that the pulse comes first, the first part comes first, and then next 3 steps, no pulse comes in. So when the pulse number 1 comes in, the memristor sets. So the current increases, but with increasing time, because no pulses comes in, the conductance or read current keep decreases, and at the end of the measurement or the process, you got this sort of current. Okay. Now, interesting thing is that if you have the same number of pulse 1, but this pulse comes in at the second step, so 0, 1, 0, 0. Now, because first step you don't apply any pulse, you still have a very low current. Now, at the first, when the first pulse comes in, the conductance goes up, and then during the second and third pulse step, no pulse comes in, so the current decays. So even though we have single 1 pulses for 2 cases, we have slightly different current when you read out at a certain moment, at a certain indicated period of time. Well, if you think about the same thing with, let's say, this signal, even though the same only one pulse comes in, you end up with an even higher current. Okay, so this sort of characteristic can give you the time-dependent, it gives you the ability to process the time-dependent inputs. What I'm saying is that for these 3 cases, you see, only 1 pulse comes in, but the timing for the pulse comes in are different. Then you come up with different currents. So if you do the similar thing with, let's say, 2 1s like these 2, or 3 1s like these 2, you all have a different currents at the end of the pulse sequence. So this is the way how they can process the time-dependent data. Now, in this case, you see this and this contains only one pulses, but they have different locations of one. If you convert this into this kind of pulse sequences, then you can end up with a different pulse timing. And then this sort of volatile nature of the memristor can recognize the different timing of the pulse comes in. So that's the very fundamental operation principle of how this reservoir type computing works. So reservoir requires time-dependent memory property. So that's very useful. And then several other works has published following this work. But some of the problem is like this. So if I summarize what I just mentioned, here we have inputs. Now, if you input this, these are the inputs. If you put these inputs into your reservoir, your reservoir transforms your inputs into higher dimensional space with nonlinear transformation. Here, nonlinear transformation means that if it's linear, it doesn't matter when it comes in, because it's a nonlinear. You can count on the timing of different pulses. But our starting point, our question was whether only this time-dependent feature of the memristor is the only viable option to make this kind of nonlinear transformation into high-dimensional space of the input. So is there any other physical reservoir or more generally the kernel which can do the same functionality? That was our question. And the reason was very simple. If you go back here, see this timing scale here is about 100 milliseconds. So it works very slowly. So if that span, the distance between the pulses, let's say microseconds, it doesn't matter because it's still always stayed here. So if you have to rely upon the physical property of the given memristor, you cannot control the time constant of your inputs, or you cannot control the response time over your system depending on input. So if your input comes in very rapidly, like time constant of microseconds or nanosecond, this kind of memristor cannot discriminate this kind of time-dependent inputs, because always the much shorter time constant means that your memristor always stays at this point. So we want to change the time constant of our hardware system as we wish. So one of the mechanisms how this memristor varies its conductance with time is like this. So you have if you have very weak filaments, then as time goes by, this interface energy disrupts the filaments, and then you have lower conductance, something like this. So our motivation, our starting point was something like this. Now we want to use the memristor. In this case, the memristor is non-volatile. It doesn't have any time-dependent conductance variation. But we could vary the time constant of the system by adding up the capacitor and resistor to this memristor like this. So if I draw the structure of the circuit schematically, here is your memristor, here's our memristor, and this memristor has a serial connection to the parallel of capacitor and resistor. Actually, it's a variable resistor and variable capacitor. When we use this kind of circuit components, we can vary the time constant of the circuits by varying C and R. And the good idea of my student, Mr. Zhang, was that when we vary the time constant of this system, we can vary the conductance of this memristor. So let me explain how we can do this. So it's basically, it depends on the RC time constant of this circuit components. Before I go there, let me explain what is our memristor is. We use the hafnium oxide-based thin film, which is ground on titanium nitride bottom electrode by ALD, and the thickness is typically 3 to 4 nanometers, and we use the tungsten top electrode. And this is the sort of chemical analysis results, and it doesn't matter here very much. So let me just skip over here. And then it shows this kind of bipolar switching type behavior. So it shows almost forming free behavior. So you see the first sweep and second sweep shows almost identical IV curves. And after confirming the uniformity of the memristor up to 100 cycles of DC cycling, we check this AC cycling of the 10 to 9s, and then we also confirm the uniformity of the different cells and sort of different sizes. So we basically made a kind of a crossbar array device. Okay, now this view graph shows the critical idea of how our device works. So here, this is our memristor, and this is our edit capacitor and the resistor. So you can actually vary the capacitance value of this capacitor and this load resistor, whatever you want. And these two are just kind of parasitic resistor, which is related to the oscilloscope to measure the potential at this point. And this is the parasitic internal resistance of our pulse generator. Okay, now during the programming stage, programming means that we input the voltage pulse like 0, 1, 0, 1, 1, or 1, 0, 1, 0, 1, something like this. During this pulse application step, we disconnect this part, parameter analyzer, and then we do something with this kind of things. And then once this is over, we monitored this device resistance using this semiconductor parameter analyzer. Now, what you can expect is something like this. Because at the first step, we don't apply any bias. So pulse generator does not generate any pulse. At the second step, we apply a pulse. Now, what you can expect is that because you have this capacitor here, so during this pulse application, the capacitor charging current flows because the memristor is not a complete insulator. It still leaks the current. So this peak corresponds to the charging of the capacitor. Now, when this pulse goes down, okay, pulse is turned off, you have this discharging current. In this case, discharging current can flow through this parasitic load resistance. And then the third step, you apply no bias. So there is nothing happen. But in the fourth step, you apply another bias too. Then, because this capacitor was discharged during this third step, there can be the charging current flow again flows. Now, if you see the voltage variation across this capacitor using this oscilloscope internal resistor, you see something like this. So first, you see this charging, and then during the third step, the capacitor discharges because there is no pulse comes in, and then the fourth step, the capacitor charges again, and then you see this charging current. Now, a very interesting finding is that in the first step, even if you apply the same voltage pulses, you see a very high peak current, high charging current, because initially the capacitor is fully empty. Now, during the third step, as you see, because of the timing that we assigned, given the load resistance resistor, the resistance value of the load resistor the capacitor was not fully discharged. So you see the voltage was maintained somehow at this point. Now when this force voltage pulse comes in, because of this not fully discharged configuration of the capacitor, the charging current flows with a small amount compared with the first one. So we have a smaller impact of current flow to this memristor. Okay, now the fifth, when the fifth pulse comes in, you see there is no current flows, no peak current flows, because the capacitor was not discharged at all, because there is no gap between these two pulses. So there is no discharging here. So there is almost no charging current. So if you see this input, among the 5 time span, we have 3 inputs, 3 1 inputs, but each of these 3 inputs produces different responses, different effects to the system. And then the memristor, the conductance of the memristor is controlled by the current flows. So in this case, the high peak current, the conductance increases rapidly, but in this case, because of smaller current flow, the increase of conductance should be smaller than the previous case. Now, if for the third pulses, even though we apply the same pulse, because there is no current flow, I mean no pulse current induced, almost no change in the conductance. Now, if you compare this this with this, so in this case, first was the first input was 1, and then 0, 1, 0, 1. Now, what you can expect is something like this, because in the first case, you have this empty capacitor, you have this strong peak, and then you have this discharging, actually partial discharging, and then third peak comes in, third voltage comes in, and then secondary peaks generate. So the device was under the almost similar inputs of up to this point. But now, after the third pulse, there is a gap between the third and the fifth pulse. You see, there is another peak comes in. So the DUT in this case should have higher conductance than the previous case, even though we have identically, you have the same 3 inputs, 3 input pulses. So that's the key point. So then what you can expect is that, okay, if you want to change these peak shapes or heights, you can change the capacitance. So if the capacitance is large, we can have higher peak current. Or if we increase this load resistance, then the discharging speed even gets slower, and then the discharging becomes even lower. Or if the resistance become here becomes smaller, then we have faster discharging. So all these variations, all these varying parameters can give us different responses of the system to the given pulse voltages. And we can also think about the time gap between the pulses. So how long we assign the gap between the pulses, or even the pulse length. You see, we can change the input to the DUT, and then we can expect something different responses of the DUT after these operations. So now we did something interesting here. Now, from here, we took these 4 inputs from 0002, 1111, and then there should be 16 inputs. And then we assign load resistance with the 1 mega ohm, and we input 4 volt height with the 200 microsecond pulses with the same gap between the pulses. And then at the final, we add the reference pulse. So now, after these different input signals, we found that the memristor showed 3 different groups of resistance, although we have 16 different inputs. and we checked something like this. So from this 1, 2, 3, 4, 5 input patterns, we found that there is only one peak, because all these inputs have effectively only one peak charging current. Because even though, yes, we have 3 consecutive pulses or 4 consecutive pulses, there is no gap between the pulses. So there is no current peaks. So effectively, even though we apply different pulses, number of pulses, the effective number of pulses only one, the first one signals. So I didn't mention this one. We always add final ones to make some sort of reference pulses. So in this case, we didn't apply any pulse, but the reference, final reference one, I didn't put the number here, but this reference one gives only one peak, and 1, 1 gives one peak, 1, 1, 1 gives only one peak. So all these 5 different inputs give net 1 spike, and this net 1 spike gives us the lowest conductance of the memristor. Okay, now the other this gives actually 2 net spikes, and then these 2 net spikes gives this value of current, and 3 net spikes, in this case only 1, 0, 1, 0, gives the highest conductance. So this is interesting, but we can immediately understand that, okay, this is not good, because these different 5 different inputs cannot be discerned from each other. These cannot be discerned each other. Okay, so can we change this worst situation into better? So in this case, we simply changed this load resistance value from 1 mega ohm to 120 kilo ohm. This actually should discharge the charged current, charged amount of the charge in capacitor rapidly, and we should have a faster decrease of the voltage here, so we can expect an even more efficient pulsing of the current. So by changing this value, and in this case, we can also change the voltage pulse width, and then we come up with this kind of slightly different responses. So even for the 1 net spikes, we come up with different resistance values. So we think that we can use this kind of property of the circuit to discern, to use, to see the different numbers of MNIST dataset. So if I summarize what we have done using these different sets of variables, so for example, the condition A is, let's say, RL was 1 mega ohm, 4 volt, 100 microsecond, and reference pulses, something like this. And then we come up with this kind of distributions. So all these cannot be discerned, so it's not good. Now we changed the condition from A to B, we come up with this, but still not very good. And if we change it to C, well, this is something like this. So finally, when we pick up this kind of conditions, so it's kind of heuristic determination process, we come up with this. Okay, so the different inputs give us different outputs. So this is going to be useful to identify different inputs. So we want to use this system to discriminate or convert the raw data of MNIST dataset to a high dimensional space of the physical kernel. Before that, we checked which kind of property we should pick up to more effectively do the job. So we checked if we what we did is something like this. We take this image here, and then first we binarize it to 1 and 0, And then we chopped the images into 1x4 vectors. So in this case, 0, 0, 0, 0, 0, 0, 0, and sort of things. So if you take this one, this should be 1, 1, 1, 0, something like that. So we have 4 element vectors, 196 of these 4 element vectors. And we want to check what kind of the vector is more important. So we checked how many these vectors are encountered when we convert all the 60,000 the MNIST dataset into this kind of 4 element vectors. And we see that we can immediately see that the 0001 is the highest. So this is evident because almost all the area is empty in the numbers. So this among all the 16 different combinations, this one is the highest. So 77%. And many of these contains very low percentage. So we don't have to worry about this kind of inputs. So we worry about only these, only the inputs with the red letters. So you want to discriminate these inputs with the red letters. So those red letters corresponds to these signals, these inputs. So 1, 2, 3, 7, 8, and sort of things. So we want to discriminate those inputs while the other inputs are disregarded because their percentage is very low. Okay. So we set the device parameters like capacitance and the resistance and the pulse height, width, length to see these inputs very well. And then we input these 4 element vectors into 160 these kind of memristor devices like we see. Then we come up with memristor conductance vector. Okay. Then this 196 by 1 by 1 memristor conductance vector should be identified by this readout layer. Then this kind of standard neural network work. Okay, now with this study, we come up with this kind of accuracy. So in this case, we use a single layer, readout layer, and then we come up with this 90%. When we compare our result with others, like Wei Ru's work or Joshua Young's work, we have a slightly better accuracy. But the most critical feature of our work compared with others is that we could use much shorter time scale because we can change the time constant of our system, our 1M, 1C, 1R system by varying the components of this capacitance and resistors. So in this case, we can decrease like 1 microsecond of time constant. Now, if we use a bit better FCN, we could increase the accuracy to 95%. Now, the beauty, the critical merit of this work, this kind of circuitry is that because we can change or we can shorten the time period of applying the bias voltage or measuring the current, we can decrease the energy consumption. So if we compare our work with others' previous works, our energy consumption is less than 1% of what the previous work has done. And then we have to think about how to integrate the memristor, capacitor, and the resistor into kind of array area. So if you use this sort of 3-dimensional structure, can minimize the area consumption. But that's that hasn't been done yet. Okay, now the second most critical feature of this kind of kernel system is like this. So this is the way how this breast cancer is detected by ultrasonic system. So this is conventional system where the pulse generator inputs the signal into the transducer, and then the transducer produces kind of ultrasound signal, and then the signal is collected to make this kind of entire image. And then this entire image is analyzed by standard neural network. So that's how the conventional system works. Now, if we have this time varying system, time-dependent kernel dynamics, we could do some sort of real-time analysis. So what I'm saying is that this transducer is something like this. If when you scan the transducer over your chest, when the transducer scans one line, it actually produces this kind of signals. Okay, so when it doesn't hit any abnormal, it doesn't produce any signal. But when it hits some problem, some malignant things, it starts to show this kind of big signals. And actually, when this transducer scans, the signal moves in this way. So each time when you process this kind of time-dependent signal, you can do the same image analysis real time. So when you get this kind of one line of signals, you can input this into your memristor, as we have done for this case, or in here, like this. And then you can get some sort of output signal in the end. And if you scan this line into some other directions, you keep getting this kind of signals, but with different time scales. So then you can the real-time image the breast cancer image. In this case, because of this the ultrasound, the signal frequency was 1 megahertz, so it's very high. So in order to process this very high frequency, then you have to have this very small capacitance and a very small resistance of load resistor. So, but you can do that because of this capability of varying the capacitance and resistance independently from the memristor. We can do the same thing for this the electrocardiogram, which is a signal from your heart. Now, for the regular output from the heart, well, you have this regular beats from your heart. But if you have some problem or arrhythmia, you have this sort of irregularities. So now, if you monitor your output with your the memristor, you see these kind of things. So as I mentioned before, the key feature of this memristor or kernel system is to detect time difference between the pulses. So if you have regular pulses, you end up with this kind of current. But if you have irregular pulses, so you can imagine that, okay, this peak will give, this pulse will give a higher charging current. Then you will end up with a higher current. So you see this kind of higher current. So as the number of the irregular beats or irregular pulse from your heart increases, you have a higher current increase. Okay, now the critical feature of this system is that you see this heart beat rate is about hertz. So it's a 10 to the 7th order of different in the frequency range or time constant that you can handle with a single system. So that's the most critical feature of our kernel system compared with the previous or conventional RC system, which uses the dynamics of memristor's own property. So we are now, up to this point, it's almost the simulations. We make only one this device and then put this device structure into computer and then do the simulations. Now we try to make this kind of integrated structure using this is our memristor, as I mentioned. We want to use this as the resistor, and we want to make this kind of capacitor for this 1M, 1R, 1C type physical kernel. So if you think about how to use this kind of things, you can detect biosignals, as I mentioned, or see actually this financial prediction can be made because this is stock market trend, and it depends on the timing. So we can detect the variation of the market trends using these kind of things. So normally we want to use the memristor as the vector matrix multiplication, the physical device of vector matrix multiplication. But in this work, we wanted to show that the memristor can be used as some sort of filter to convert the time-dependent image into a non-linearly transformed higher dimensional space that can be utilized to represent the original image with better characteristics as what the CNN is doing for static devices, static images. So if I summarize what I just talked about, okay, we did kernel type application of our memristor. Well, actually, the original starting point of this work was that when we tried to use the memristor as the conventional vector matrix multiplication element, we always have to worry about this variation and the wire resistance and the nonlinearity of the conductance. So we started to think about, can we use the memristor in a different way? And then we come up with this kind of idea that, okay, this can be used as a temporal kernel, which is not reservoir, because we don't use a time-dependent variation of the memristor, but it's still a kind of a physical or temporal physical kernel that can produce the time-dependent data. So we can we demonstrate that we can use this system to identify or to recognize the MNIST data set with a better performance than the previous reservoir-based system. And we can use this system for medical diagnosis with a very different time constants. So if we apply, if we're smart enough, we can apply the same system to other things like financial stock markets or something like that. Okay, with that, thank you very much for your kind attention, and I will be happy to take any questions or comments.